G'day chemistry students. In this video we're going to be looking at building on what we already know about the dilution concept and completing some calculations. Now in particular, in the previous video I did a dilution with some copper sulfate solution that I prepared, and so I'll be doing some calculations to find the new concentration of the substance or the solution that I produced. So this is, I guess, just a written version of what I did. I had 25 mils of 0.1 molar copper sulfate solution, and I transferred it to a 100 ml volumetric flask. I then filled the flask to the 100 ml graduation, and there's a new concentration. And so what we're going to be doing is calculating that today. Now, first off, what I'm going to do is clarify a pretty big misconception, and that is that when we're doing our calculations, we care about the original flask itself, and this is not the case. So when we are doing one of these dilution calculations, what we actually care about is the solution that's come out of the pipette itself. So what you'll notice is that these two concentrations are the same. Reason being, I had my solution 1, or my first solution. It had a set concentration, and when I pull some of that solution out, the concentration still remains the same. It's like saying that concentrated dark cordial, if I pour some of it into another container, the concentration of the two cordials in both containers are the same. Same principle here. The concentration doesn't change when I transfer it from one to another or separate it into two parts. What we care about, though, is the volume of the solution that's in the pipette, because that's all of the solution that ends up in the second flask like we've got over here. So what you'll notice is that we have C and V for the pipette, and C and V for the volumetric flask. Now, we always know the C and V out of the pipette, and usually we label them as C1 and V1. What we don't know is C2, the concentration or the new concentration of the new and diluted solution, but we do know the volume. Now, using these concepts, I'm going to be showing you sort of some equations that might come out of this and some concepts that come out of this, but I'll do that on paper. Let's get over there. All right, so quick reminder, we have C1 and V1. They reference measurements from the solution in the volumetric pipette. We also have C2 and V2, which represent the measurements for the new or diluted solution. Now, what you'll notice is that C2 is missing because what we're trying to find out is the new concentration of the new solution. There are two ways to solve a problem like this. I'm going to go through the longer version first, which is probably a little bit easier conceptually. And then I'm going to move on to a different way of solving the problem, which is a little bit faster. But if you're going to be using this equation effectively, then your conceptual understanding of dilutions themselves have to be pretty up to scratch. But anyway, let's get started. So first off, what I'm going to do is I'm going to figure out the number of moles in the volumetric pipette. What I want to find is N1. The number of moles of copper sulfate in the volumetric pipette. And the reason is that N1, the number of moles of copper sulfate in the volumetric pipette, I keep saying that over and over again, but it's really, really important, is always going to be the same as N2, the number of moles of copper sulfate in the new or diluted solution. Now, the reason is, in the new flask, the only source of copper sulfate particles is from the volumetric pipette. Because remember, with the new and diluted or diluted solution, what we're doing is mixing the solution that was in the volumetric pipette, the 25 mils of it, and the remaining part of the mixture is simply water. So the only copper sulfate particles have come from this guy, the solution in the pipette. Which means that the number of moles or the number of particles of copper sulfate is exactly the same in both containers. Knowing this, we can do a little bit of math to first find out what is N1. Once we know what N1 is, we can say that they're exactly the same. Once we have N2, what we should be able to do is calculate for C2. And I'm going to show you how to do that now. So what we know is that C is always equal to N over V. And what I can do is rearrange my equation to make N the subject, because for this first equation, what I want to do is find N1. So N1 will be equal to C1 times V1. To substitute those numbers in, that is going to be N1 is equal to 0.1 times 0.0250. And what that should be at the end is 0.00250 moles. I'm just doing this really quickly with some mental math. It's as simple as putting it in a calculator, though, if you needed to do that. Just going to bring my working up here. So the next part, what we said was that N1 was equal to N2. Now, if N1 is equal to 0.0025 moles, then N2 is exactly the same as well. So N2 is equal to 0.0025 moles. Now, the last part, what we want to try and do is find the new concentration C2, just so I'm saving space and so that you can see each of the parts really clearly. I am working across the page. Preferably you'd be working down the page, but anyway, so again, we have C equals N over V, which means C2 is equal to N2, the number of moles that's in our volumetric flask, the number of moles of copper sulfate in particular, divided by V2, the volume of the solution itself. So C2 is going to be equal to 0.0025 moles divided by the new volume, which is 0.1 liters. And that data has just come from here and here. And to calculate for C2, that would be equal to 0.025 moles per liter. And that would be our concentration. Now, there is another way, as I said before, another way of doing this calculation as well. So I'm just going to show you that one really quickly. And to do that, I'm going to do a little bit of algebra to derive or prove the equation that we're going to be using. So we know that N1 is equal to C1 times V1. That's just come from this equation here when I rearranged before. We also know, and I've written this already, C2 is equal to N2 over V2. And if I was to rearrange to make N the subject, I could also write this second equation as N2 is equal to C2 times V2. Now, what we should see is that there are some similarities between these two equations. They have exactly the same structure, and what we also know is that N1 is equal to N2. If N1 is equal to N2, then they both must also equal C1 times V1. And all of those also equal C2 times V2. Some simple algebra, but pretty powerful if you are able to understand what's going on and how I'm doing it. If you're a little bit confused at this point, then by all means, come and ask me in class over the next couple of days, and we can work on trying to figure out why this works. But this is really powerful because now what we know is that C1 V1 is equal to C2 V2. And if I look at some of the data that I have up the top, and I'll just move this down so we can actually see, we know C1 and V1. We know V2. So we have C1 and V1 as known quantities. V2 is another known quantity. The only thing that's missing is C2, and we can rearrange this equation to be able to calculate for C2. So I can say that C2 is equal to C1 V1 divided by V2. And all I would have to do is substitute in my values from here. So C1 is equal to 0.1. V1 is 0.0250. And all of that is being divided by V2, which is 0.10. I mean, even for us, these cancel out. Like, you wouldn't even have to use a calculator for this calculation. but you could. That's completely fine. And if C1 and V2 weren't exactly the same number, then you would have to use a calculator for this. But we should see that 0.025 moles per litre is our final answer at the end. Now, one more thing to add, and something that I didn't talk about in the first solution that I did, what we need to keep in mind is that this value here, 0.01, only has one significant figure. And so unless we knew that value to a higher degree of accuracy to more significant figures, then our final answer would also have to reflect that as well. So I'm going to be rounding this up to 0.03 moles per litre, as the value that I gave at the beginning of the practice question only had one significant figure to begin with. But anyway, that's dilution calculations. There are lots of different versions of these calculations. You might have to work backwards. You might know what the end concentration for the dilution is, or maybe you know what concentration you want it to be when you dilute, but you have to try and figure out the starting concentration of the solution that you need, or the new volume that you're going to have to make, or something like that. But they all work using this one equation. But anyway, we can do more of that when we get into doing some of those practice questions in the next week or so in class. Thank you very much, everyone. We're quickly approaching the end of Module 2. Now, there's one more section left in the syllabus, which should cover about a week's worth of work. We're going to be looking at gas laws, so applying some quantitative principles to gases themselves. But until then, have a good one.